flips of the past, because lava lines up with the magnetic field as it solidifies. The problem is, flips aren't regular. To predict the next one, we must know what's going on in the core.
Okay, going to spin to 10 RPS.
We have two different types of experiments that we're currently working on. In the first experiment, we actually drive propellers that churn the fluid, propeller on either side, that sets up this sort of wildly turbulent flow.
Okay, getting ready to run at 10 RPS.
Ready to go.
At the heart of Dan Lathrop's dynamo is a sphere filled with hot sodium. Electrically, sodium behaves like molten iron, but it's 1,000 degrees cooler. A propeller creates the sort of turbulence thought to be caused by the rotation of the Earth. Up to now, they haven't been able to generate a steady amount of magnetism, but they have learned that small changes in speed and temperature significantly affect the magnetic field.
In the other experiment, we have a geometry very close to the Earth's outer core, where we rapidly rotate a sphere, which has a layer of liquid metal, and then we heat the outer edge and cool the inner sphere and set up convection, sort of like you might have boiling in a pot making pasta. In this case, it's sort of the churning of the liquid metal that gives rise to a turbulent flow that affects the magnetic field.
The next step is to build a bigger model. After all, the real Earth's core is over 4,000 miles in diameter.
There are really three main questions that we're trying to understand in the experiments. We'd like to know what sets how strong the Earth's magnetic field is. We also would really like to understand what causes them and be able to predict them. And the last thing is we'd like to know what are the limits to having a dynamo on a planet. So why does the Earth have a dynamo and Venus does not?
Einstein insisted the question of how the Earth generates so much magnetism was the most important unsolved puzzle of physics. No one knows when the next reversal will happen. One thing is certain, though. The magnetic poles will reverse. Scientists in Verne's day knew that magnetism came from within the Earth, but not about magnetic reversals. Yet he predicted a magnetic flip. His explorers had been traveling for months. Professor Lidenbrock reckoned they were almost at the center of the Earth. They stopped to draw breath and take a bearing. That's when they realized something was wrong. Their compass had gone crazy. Had Verne seen into the future again? He certainly knew of the connection between magnetism and electricity because he tells us that the compass flip occurred during the storm at sea, when lightning struck the boat. Don't try this at home. Fortunately, this isn't the only way to find out when the volcano's going to blow. Volcanoes are the richest source of rock from deep inside the Earth. The most active is in Hawaii. This is the closest we can get to what it's like at the center of the Earth. It's a reminder of the heat and power hidden beneath the surface of our planet. Kilauea volcano has been spewing out lava for thousands of years without a let-up. It single-handedly built the island. Molten rock, called magma, surges up from near the Earth's core and blazes through the crust. The stream, known as a plume, lets inner Earth let off steam. It's like a safety valve.
We believe that the volcanism at Hawaii is ultimately caused by a hot plume rising up beneath it, which occurs because material at the bottom of the mantle is heated up by the core. The core's maybe 2,000 degrees C hotter. And heating it up causes it to become less dense, and then it rises through the mantle. A good analogy is with a lava lamp that you might see in someone's living room.
It's lamps like this that show us what's going on in the Earth's mantle, the layer between the core and the crust. Rock, heated by the core, rises while cooler material sinks from the surface. It's this never-ending process known as convection that pushes magma to the surface, where it erupts as lava.
Hawaii is a bit of a special example. It's the most active island volcano that there is. It erupts with extreme frequency, and it's also exceptionally runny, and so the lava flows tend to move very fast. And they have a high proportion of these so-called pahoehoe surfaces, which are these beautiful, smooth, ropey textures that you see.
Lava can build, but it can also destroy. It can seldom be diverted, and it wipes out anything and anyone that gets in its way. Early geologists assumed that such torrents of molten rock flowing out of volcanoes must leave huge voids and caverns behind them. Jules Verne's explorers followed one of these lava tubes as they approached the center of the Earth. But the Earth had one last surprise in store for them. As the professor, Axel, and Hans neared the center, their path was blocked by a rock fall. There was no other route, so they decided to blast their way through. Verne knew very well that molten rock trapped deep in the Earth is under huge pressure. If that pressure is released, it can start a volcano. That's why blasting was a risk. In classic literary tradition, the eruption they triggered blasted our heroes to the surface without as much as a singed eyelash. Eruptions are how the Earth recycles itself. Convection currents in the mantle carry rock to volcanic vents and fire it back to the surface. Volcanologists today can't get inside an active volcano, but they get up close. Tim Elliott plays his part 8,000 miles away.
As geochemists, we tend to come in after the thing's cooled down and then knock bits off.
Predicting eruptions is every volcanologist's aim, but it makes predicting the weather look easy. Lava samples tell us that the Earth's composition is complex, and it changes whenever a large earthquake or eruption occurs. For Tim Elliott, who struggles to keep tabs on this shifting underground world, every sample is a rich source of information. For what will eventually be a highly sophisticated piece of analysis, Tim starts by crushing the lava in a machine Jules Verne might well have designed himself. The first thing is to break the lava into pieces. Then it must be crushed into a fine powder. The next step must be done with great care. The hydrofluoric acid Tim uses to dissolve the powder is equally good at dissolving skin and bone. It eats all the rocky parts away, leaving just the base elements. Those are the parts Tim's interested in. The lava sample is heated and the acid evaporated off overnight.
Once we've got a pure separate of the element that we want, we then take that to the mass spectrometer to analyze its isotope ratio.
Wherever they come from, any two samples of a chemical element will be chemically identical. But we now know that they can differ physically. A mass spectrometer can tell them apart and tell Tim just where in the Earth a sample came from. This one came from very deep indeed.
So that maybe gives us a clue that these things come all the way from the core mantle boundary. But in terms of the ultimate depth of these things, to some extent, I hate to admit it, we rely on the seismologists.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Seismologists can see inside the Earth without going there. Their explosions create shock waves of sound. When the waves hit rock, they bounce back to sensors on the surface. Since different rocks reflect waves at different speeds, seismology lets us map the Earth's subsurface landscapes. Can today's technology take us to the center of the Earth? If so, what would we find there? Seismology lets us see with sound. And there's more to it than creating big bangs, as MIT's Rob van der Hilst explains.
Seismology is pretty much the only way to get fairly direct probes of the Earth's interior. And there's a lot of development in the seismic theory and observational seismology itself to really give much more refined images.
Seismology is similar to an ultrasound scan that can show an unborn baby in its mother's womb. An image can be created because sound travels through different parts of our body at different speeds. Unlike this scanner, which generates its own sound, seismology can make use of natural sounds that occur every minute or two. The sound of earthquakes. Thankfully, we don't notice most of them, but there are actually 1 million a year. And they're shaking up our ideas about what's going on thousands of miles beneath our feet. Earthquakes are appallingly destructive to human life, but to scientists, they have their uses. The seismic waves are like sonar. By listening as they pass through the Earth, a picture can be built up of a place no one can ever see. First, the waves race through the crust, the skin on the planet's surface. In some places, only 4 miles separates us from the intolerable heat of the magma in the interior of the Earth. The temperature is nearly 3,000 degrees, so intense that the rocks are partially melted. 3,000 miles down in the core itself, the temperature reaches an unimaginable 7,000 degrees. It is the ultimate nuclear reactor, the engine driving the planet.
What we can really image very well is the material that goes down. And in some cases, we can see down to the core mantle boundary. And all that information tells us a little bit about, how density is concentrated in the center of the Earth and how density changes with increasing depth.
Seismologists image rocks. Petrologists make them, mimicking the heat and pressure of the deep Earth.
Now we know where they come from, we know how deep they come from, because the minerals contain elements like calcium and aluminium, and the distribution of these elements between the different minerals depends on pressure. So by simulating the pressure, taking a sample like this and subjecting it to high pressure, and seeing how the compositions of the minerals change as we change the pressure, we can go back and work out what depth this particular sample came from.
The anvil on which Bernie forges his man-made minerals is made of tungsten carbide, a material so hard we use it to make drills. He puts a tiny sample of rock in a ceramic tube, a miniature furnace, and then walls it up. The bricks are specially shaped to focus the force he'll apply to them. This way, he aims to reproduce the massive pressures to be found in the Earth.
Over a period of about 4 or 5 hours, we raised the force to around 500 tons, and we then apply a current to the furnace, which is in the middle of that lot, in order to raise the temperature to 1,700 degrees C.
The petrologist awaits the outcome as anxiously as a pizza chef. If the heat and pressure are right, the elements will fuse together into an exact copy of the mineral he's studying. This tells him where it came from. In this case, 440 miles down, where the pressure is 250,000 times higher than at the surface. The advances in science since Verne's time have been breathtaking. And we're still discovering how the Earth was made and how it continues to change. We've come a long way, not in distance, but in knowledge. We've ventured 200,000 miles into space, but as yet, we've only been 7 miles into our own planet. With all the knowledge and technology we have today, surely we can tunnel to the center of the Earth. If we could tunnel to the core, the rewards would be huge. We could shut down our power stations. The energy we tap into would never run out. It would be free and cause no emissions. We could dispose of dangerous waste in the world's hottest incinerator. Huge quantities of minerals are there, just waiting to be brought to the surface. Maybe we could build a high-speed transportation system through the Earth, a global subway. But it's not that easy. This tunnel, linking England and France, took 5 years to construct, and it's only 30 miles long. It's 4,000 miles to the center of the Earth. And would we actually want to go there? It's an adventure that Dan Lathrop would welcome.
Well, it's an interesting idea for an adventure. I guess I'm ready to go if it becomes possible.
Meet the team that's designing the first vehicle capable of penetrating to the center of the Earth. Today's tunneling machines have brains as well as brawn. They drill and support the tunnel as they go, and never stop. But what chance has even a smart monster like this of getting to the center of the Earth? Brian Clark has built tunnels all over the world.
If we're tunneling to the center of the Earth, there are different combinations of material, but generally we would start in soft ground tunneling. We would move through into rock, and as we go to extreme depth, the rock would change in character due to the temperature effects. We almost certainly would need to use an arm with a cutter head, tungsten carbide teeth on it to grind and smash the rock.
Today's most